Hey everyone, and welcome back to this class, Deep Reinforcement Learning in Python. In this lecture, we are going to discuss the pseudocode for deep Q learning in Atari. One of the key tricks in this lecture is how to implement the replay memory efficiently. So that's the main non-trivial thing we will discuss in this lecture. From a top-down perspective, what we're doing is actually very simple. First, we create three things: our environment, our target network, and our main network. Then, in a loop, we just play the game for a predetermined number of episodes. Now, we can look more in depth at what playing the game for each episode entails. As you've seen, this means we're going to run a loop that quits when we see the done flag. Inside the loop, we're going to take an action depending on the current state. Of course, we use the neural network to determine which action to take using an epsilon greedy policy. This gives us back the next frame, the reward, and the done flag. Using the next frame, we can append that to our state to get the next state for the next iteration of the loop. We also want to store the SARS prime tuple in our experience replay memory. Lastly, on each step, we're going to call the learn function. We also want to make sure that we periodically copy the weights from the main network to the target network. So what goes inside the learn function? Well, this is where we actually train our model. In this function, we're going to grab a random batch of samples from our experience replay memory. This is a batch of SARS prime and done tuples. If you recall, the S's form the inputs into the neural network. The targets are calculated using the target network. In particular, the target for a given Rn S prime is R plus gamma times the max over A prime of Q of S prime A prime. It's important to remember that if the done flag is true, that means S prime is a terminal state, in which case the target is just R, the reward. Then we update the parameters of the main network using the squared error between the prediction and the target. So that's essentially it. The main trick in the upcoming code is how to efficiently implement the replay memory. Imagine if we just naively stored each SARS prime done tuple. If you recall, each state, whether it's S or S prime, is a 4 by 80 by 80 array. That's a pretty big array. But not only that, we're going to have multiple of these arrays. Let's suppose we store these in lists. So when our list becomes full, we have two operations we need to do. First, we want to append the latest state, so we call the append function. Then we also want to remove the oldest state, so we call the pop function with the argument 0. Now this might appear that it takes up constant memory, but in fact it does not. Unfortunately in Python, this will cause a memory leak. What's another problem with storing states this way? Consider S and S prime. Since S prime is the state after S, the last three frames of S are equal to the first three frames of S prime. In other words, we only have 5 unique frames, but we would have to store 8 frames, which is almost double the amount we need. But our problem is even worse than that. If you recall, we're going to store these tuples at every time step. So the S prime of this time step is equal to the S of the next time step. In other words, these are totally redundant. As an exercise, you might want to try to calculate exactly how redundant this method is. How many unique frames do we have? And compared to that, how many frames do we actually end up storing? Here's the solution to this. Let's instead just store consecutive frames. Now suppose it comes time to draw a sample, meaning a tuple of SARS prime and done. We have an array of frames, actions, rewards, and done flags. Let's suppose we choose a random index t. Now, the state is stored in the frames array at the indexes t-4 up to t. The next state is stored in the frames array at the indexes t-3 to t+1. The action, reward, and done flag are all stored at index t. So you can see how we implicitly have all the states we need just by storing all the raw frames. Now, of course, there are all sorts of edge cases you have to deal with. For example, what happens at the boundary between episodes? We can't just look at the frames at index t-4 up to t if the index at t-2 is an episode boundary. In addition, we'll want to update the arrays in a circular fashion. This is because our array is pre-allocated and is of fixed length. So once the array is full, we'll just go back to the beginning. Another thing we have to take care of is ordering the dimensions for the library we're using. If you recall, Theano uses the ordering color by height by width, whereas TensorFlow uses the ordering height by width by color. A single frame, since it's grayscale, is just a 2D array, height by width, so our replay buffer object will have to handle creating batches of images such that the dimensions are in the correct order. Of course, these details are no good to discuss philosophically, so let's look at the code.